Hey everyone, welcome to the refresher series VLSI 101. I hope you guys have gone through our repo VLSI 101. Probably if you're watching our video right now, it means that you guys should have gone through it. Here mainly I wanted to just mention about the resource directory because it's really important. Here, these two particular resource, we want you guys to maximum make use of it. So this is basically the general textbook, which is like quite popular in computer organization and architecture. So here only you'll get all the basics right as to um, how to like design a processor and how a processor works itself. So it's such a great book by David Patterson and John Hennessy. So here, chapters 2 and 4 are like really important. So in chapter 2, you learn about the instructions itself. What is instruction? What is an instruction set architecture? And what is the ISA for MIPS 32 base instruction set? And like how to decode an assembly MIPS instruction to binary or machine instruction code. So all these things you learn in chapter 2 and chapter 4 it is more on the processor design itself. So once you get familiar with the instructions, like how are you going to execute that instruction using HDL. So you guys basically need a data path. The data path will consist of all the resources there, and that is the controller unit. So the controller unit sends all the signals there. So the data path requires all these signals to be present for it to execute an instruction the right way, decode the instruction the right way, and you'll also start from a basic implementation to pipelining them and adding some more extensions as well. But for our scope through the initial our VLSA 101 project, we want to build the MIPS 32 vanilla instruction set, which I'll just show it like what I mean by that now. And I just want it to be a single cycle core. So the second resource which I wanted to talk where I'll show you uh, the instructions which you want to execute is the MIPS reference data. So this MIPS reference sheet is really important for you guys to like quickly refer and quickly design your processor. So whatever is there on the left side, that is a core instruction set you guys can see here, or the base instruction set. So the first column, it's the name of instruction or the mnemonic there. So it will have all the like assembly is MIPS assembly, all those assembly instructions which is being supported under core instruction set, and you'll find the instruction format as the second column. So under the last column you'll see opcode slash function. So for R type, generally opcode is 0, and the function, if you see according to the official MIPS thing, uh, official MIP documentation, these are the functions that are the functional codes that are being used. For I type and J type, you'll see it's just the opcode, and the opcode itself differs from instruction to instruction. And these are all the flags and other, control registers, you can say, which will come into use much later on. Uh, Only like few things we'll have to worry for now, like the overflow and the zero flags and everything. Uh, all those things in later weeks when you design it, you'll understand it much better. And this is the decoding part for different type of instructions. So we will actually do quite a bit more than this also. You can refer to the computer organization book itself. There is a big table with all those. So, like again, that is we'll give you the table next like the upcoming week in the upcoming week resources. Whatever is there on the right side, for now we are not touching them. They are all like extensions of our base processor, right? So for now, if you know this much, you are well and good to start. And I hope you guys are done with downloading the Mars IDE. So I think our first exercise was to download and set your Mars ID. Once that is done, we gave you like two like programs to write in MIPS assembly. We felt those two will cover a lot of cases, and if you are able to code those two and understand them, it will be good enough for you guys to get started with designing the processor itself. So I think the first task was to code greatest common divisor or greatest common factor using MIPS assembly code, and the next one was doing the permutation operation, right? So I think the Mars ID link could lead you to this page, right? So there, if you guys go to download, you guys should able to view this download Mars at the top. If you press there, you'll find the Java executable file. So I have already saved it, so I don't require it right now. And here you guys also need to download Java 1.5 SDK or later to support this particular uh, application. I have all those things set up already. If you guys face any issue, put it in our main community chat itself. WhatsApp link has been provided. Okay. Now first, let me open the IDE. So this is the command to run a Java executable file. So now the IDE will open up, right? So now I want to, load both the programs that we guys have written to just show it to you. There's no one single way to do it. We'd also love to see what you guys have written. If your code is, if you guys feel your code is, much efficient, please feel free to, pull up PR. Another goal is to also get you guys introduced to open source contribution. A small thing which we guys thought we could do is, uh, put the whole project on GitHub, and also like allow you guys to pull PRs, and also add on to the resource. You guys could also be a part of it as you guys move, right? So here's the greatest common factor here. So here I know it's not very visible. So let me open up using my command line editor, Neogum. Yes. So here, basically, what I have done is I have defined a data array. So the first, number here signifies how many pairs of uh, numbers on which we are going to perform this greatest common factor. So here I have just taken a pair of numbers. I thought this will be the basic thing which we could do. If you guys want to do like threes or fours to which you want to find the greatest common factor, please do it. You can also pull a PR. You can also contribute there. We'll be more than happy to merge it. So here, the main program part, basically what we are doing is we are first loading the address of the data array in our register T7. So once we load that address, whatever is present with that address, we are just using load word. So LA is basically load address. So your load word, what it does is it takes the value at and zero is the offset, by the way. It takes the value from register T7 and it loads in register T5. And here, add immediate instruction we guys are using. Basically, we are loading value 4 in our register 8 and 2 in like this particular register. And we are again to store the result. We are taking wherever the data array is there, and we are adding to the address plus 200, right? We like always add in multiples of fours, by the way, because here it's 32 bit, word is 32 bit. So we guys want to like not no overlap for each uh like location, you have to like increment it by 4. So that's also the same reason why I have saved 4 and registered T8. So here is a loop statement. So basically, what I'm trying to do is I'm trying to uh, keep an uh, you know register S2 the smallest of the two number, and in register S3 the bigger number will be there. And also I'm storing like two more like each copy into like one extra register, which I'll be using it further on to like one side I'll keep it unmodified, and the another side I'll be using it for the computation. So yeah, and here under reminder, basically what I'm doing is here is the main logic which starts here. So in greatest common factor, you can do it in like two ways. One is the modulus method, but what I do is I have like consecutively I like subtract and check whether uh, the since we know that the first number in S2 is the smaller number, I keep subtracting S2 from S3 and check whether S3 is small is now um, like is it like still greater than like 0, and if it is greater than 0 and it is also greater than S2, then I keep looping here until it is not. So then I have like a sanity check or fail-safe mechanism for 2 alone. So sometimes in edge cases, what it happens is that if there is an odd number and there is a 2, this particular the logic which I use, like consecutive subtraction, leads to uh, a stage where uh, there's a 2 and there's an odd number, and still 2 becomes the greatest common divisor. If you guys are able to do the modulus part and give me a much better uh, like assembly code, I'll be more than happy to merge it. So that's where I go to consider, where I'll see whether if both if either of the value is odd or not. If it is odd, then since it's 2 and an odd number, I'll directly give it as 1. So reconsider is where I store it or I write the result into the main memory. So and I think yeah, another loop is the second loop. So what happens is that there will be sometimes cases where my uh, like second number is the smaller number. So I just perform a swap here, a swap operation. So then I halt it. So this usually hits all the test cases. Let us run and see. So we are running patch of 24 and 18, 49 and 21, 51 and 17, 31 and 22, 15 and 10, 7 and 0. If it is 0, if it 0 appears, then we are by default we are just giving the GCD as 0. So for 24 and 18 it's going to be 6, for 49 and 21 it's going to be 7, for 51 and 17 it's going to be 17, 31 and 22 is going to be 1, 15 and 10 is going to be 5, 7 and 0 is going to be 0. So we'll have to assemble it first here. So once it gets assembled, you'll be able to see the address where it is stored. You'll be able to see all the machine code here, and then you'll also be able to see the assembly code here. So then you guys can just run it. Since I have used, let me stop it here. Halt here, there will be an infinite loop. So within few seconds, it will probably come here. So you'll be able to see the data segment here, where like whatever was defined in data array will be still seeing here, starting from 618, and also it's given in hex by the way. So once let me go to the result where yeah, here you can see the result at 200. But 6 is here, 7 is here, it's in hex. So 11 is basically 17 in decimal, 1 is here, 5 is here, and 0 is here. So you can see that's worked well. So then let me open the next one. So the next one is the permutation operation. Okay, again I'll explain it to you guys. Okay, coming to permutation operation, again I have defined a data array. So here I just the first like number basically signifies how many the count, how many inputs are there. So and also -9 is an invalid input. Even for that edge case, you guys have to uh, you know code it accordingly. Where it gives return 0 or something. Okay, now coming to the text part where the actual code logic is there. First, again, same workflow only. I'm loading the address from data array, and then I'm loading the first one, the count value. So, and again, +4, which is you just used to increment, like go through like step by step, next address location. That's why I just add this 4 to go move to the next address location. Next is again I'm reading the data array into another register and I'm adding plus 100 in hexadecimal. So I'll be like storing it at plus 100 hexadecimal like location. There'll be a gap between the array, the input array and output array. So here's the main uh, logic running through. So first here I'm just reducing a number from the count, and if the count is 0, that's basically means we have completed the permutation. That's where it goes to halt, and halt is where we are going to stop. So at each loop in main, we are going to reduce one from the count, and we are uh, you know going to the next address location here in the add and load word, and then we are checking if uh, like if it is equal to 0. If it is equal to 0, then we are like going to skip factorial, because that's when you know that it like the value become it is 0 now, and the output is going to be 1. So and the factorial loop is here. So I have used the multiply the operation here, even though we may not program like use this model it like for future you can model. Still have just given a usage for mult, and MFLO is basically move to the uh, lower buffer. So basically what happens is multiplies if like both are 32 bits and 32 bits, so the result is going to be 64 bits. So there will be a higher buffer and lower buffer. Since like we guys know, uh, like for multiplication, we are not going to use like huge numbers. You can just load it from the lower buffer. So for like move to the lower buffer is this command I have used here for this register. So and here again I'm like reducing the count, or I'm like no, this is not a count, but I'm just uh, reducing one, and I'm just multiplying it. Here is just a factorial loop. So you will do right four if it's four exclamation 4 into 3 into 2 into 1. So for each iteration, one uh like number you like decrease it. Then I'm like storing the result. So this is the skip factorial where I just write 0 like in case if it's a negative number, or if it's an invalid number. And halt is where I have done something different. I have used something called as a system call. So this we are not going to necessarily make our uh, like core system call compatible, but I just used it to show that this is where it won't go through an infinite loop, but it's just going to halt here if I uh, make my this V0 register as 10 and I call it, it will make a system call where it will ask the program to just stop it. So I'll just execute and show. So all these you guys will be able to understand better if you guys like read through our book. I know it's a lot to take in, but yeah, assembly code to begin with, it's going to be like this. So you can see the program is finished running. So I can basically go to +100 address location here. So you can see 2, 18, and 0 in hexadecimals. which will correspond to values whatever you have taken. So 2 factorial is going to be 2, 4 factorial is going to be like 24, and that is 18 in hexadecimal. And minus 9, we have taken it as 0. Okay, so I think you guys would have gotten some idea as to how these things work. So hopefully, like, we'll guys meet you in the next week. Yeah, until then, I think meet you later then.